For 170 years, 31 Atlas drifted through the asteroid belt, 22 miles wide, dark as coal, spinning between Mars and Jupiter. Just another rock among thousands, catalogued in 1855 and largely forgotten. But in 2019, something changed. Ground-based telescopes detected an anomaly, a wobble in its rotation. Then came the spectrographic readings. Chemical signatures that shouldn't exist on a primitive asteroid. Elements that hinted at something far stranger. When astronomers cross-referenced the data, they realized the mystery was only beginning, and Atlas had been hiding in plain sight all along. 31 Atlas was first observed on March 29, 1855, by German astronomer Hermann Goldschmidt, working from a cramped Parisian rooftop with a modest 6-inch refractor. He logged it as the 31st asteroid discovered, a faint point of light drifting through Virgo. For over a century, it behaved exactly as expected. Its orbit was stable, elliptical, taking 4.6 years to circle the Sun at a distance averaging 2.6 astronomical units. Its size, estimated at roughly 22 miles across, placed it squarely among the mid-sized residents of the main belt, unremarkable in every way. By the mid-20th century, Atlas had become a footnote in astronomical catalogs, a target for periodic positional updates, but little else. Its albedo, the measure of how much light it reflects, registered low. Dark surface, likely carbon-rich, consistent with primitive material left over from the solar system's formation 4.6 billion years ago. Spectroscopic surveys in the 1980s and 90s confirmed the standard profile. Silicates, traces of water ice, organics, the usual suspects. No one looked closer. There was no reason to. Atlas was predictable, ordinary, a relic tumbling through space on a path as reliable as clockwork. It would take 164 years before that certainty began to crack. In September 2019, the Pan-STARRS Survey Telescope in Hawaii flagged an object designated 31 Atlas for follow-up observation. Routine orbital refinement, nothing unusual. But when astronomers at the Minor Planet Center processed the photometric data, something didn't align. The light curve, the pattern of brightness variation as the asteroid rotated, showed an irregular period. Not the smooth sinusoidal wave expected from a tumbling rock, but jagged, almost chaotic flicker. Teams at the European Southern Observatory trained larger instruments on the target. High-resolution spectrography revealed absorption lines that defied the standard C-type classification. Iron oxides, yes, but also chromium compounds, rare earth elements, and faint traces of technetium-99, an isotope with a half-life so short it should not exist naturally in any asteroid older than a few 100,000 years. The data sparked immediate confusion. Technetium decays too quickly to survive from the solar system's birth. Its presence implies recent formation or ongoing synthesis. Neither makes sense for a cold, inert asteroid drifting in the void for billions of years. Cross-checks against historical observations deepened the mystery. Archival plates from the 1950s showed Atlas at a slightly different position than predicted by its known orbit. The deviation was small, less than an arc-second, but enough to suggest something had altered its trajectory. Not a collision. No debris field was detected. Just a subtle, unexplained drift. By early 2020, the realization set in. Either Atlas had fundamentally changed over the past century, or the object astronomers were now observing wasn't the same one Goldschmidt had discovered in 1855. The implications hung in the silence between telescope domes. If it wasn't Atlas, then what happened to the original? And what, exactly, had taken its place? The break came in May 2021, when a team at MIT's Lincoln Laboratory Optical Communications Telescope Laboratory detected something no one anticipated. A faint, pulsed emission in the near-infrared spectrum, emanating from the region surrounding 31 Atlas. Not continuous radiation, but discrete bursts, repeating every 11.3 minutes with precision that ruled out natural processes like outgassing or thermal cycling. The signal's wavelength, 1064 nanometers, matched the output of ND, YAG lasers, a technology commonly used in satellite ranging and optical communication systems. But there were no active missions in the asteroid belt using such equipment. And even if there were, the signal's origin point didn't match any known spacecraft trajectory. It came from Atlas itself, or something very close to it. Spectral analysts parsing the bursts found structure within the pulses. Phase modulation, a technique used to encode information into light waves. The pattern wasn't random noise or interference. It carried data, organized into packets, each block separated by a 7-millisecond gap. When decoded using standard optical communication protocols, the packets yielded binary sequences that aligned into grids, geometric arrays that repeated with mathematical elegance. The grids formed tessellations, interlocking patterns of triangles and hexagons, reminiscent of crystalline lattices or molecular diagrams. But they weren't chemical structures. The ratios between segments followed Fibonacci progressions, and the overall symmetry matched quasicrystalline arrangements, patterns that don't repeat, but maintain order across infinite scales. Patterns found in exotic materials on Earth, but never before transmitted from deep space. No natural process generates quasicrystalline data transmissions. The evidence pointed to an artificial origin, but the source remained elusive. Radar imaging campaigns using the upgraded Goldstone Deep Space Network attempted to map Atlas's surface with unprecedented resolution. What returned defied every expectation. The object appeared to have no solid surface at all, just a diffuse cloud of reflective particles, too organized to be a rubble pile, too sparse to be a cohesive body, as if Atlas wasn't a rock, but a swarm, a collection of countless smaller components moving in coordinated formation. Follow-up observations captured even stranger details. The particle cloud seemed to shift configuration over time, compressing and expanding in pulses that synchronized with the infrared emissions. Thermal imaging showed no heat signature consistent with solar warming. Instead, discrete hotspots appeared and vanished across the swarm in patterns that suggested active energy distribution, not passive solar absorption. Inside the International Astronomical Union's Minor Planet Center, the mood shifted from curiosity to concern. Access to the latest observational data on 31 Atlas was suddenly restricted, with new security protocols implemented overnight. Observers who had been tracking the object for months found their telescope time requests denied without explanation. Internal communications, once open and collaborative, were now routed through encrypted channels. A task force was quietly assembled, drawing members from NASA's Planetary Defense Coordination Office, the European Space Agency's Near-Earth Object Coordination Center, and DARPA's Tactical Technology Office. The group operated under the designation A31X, a code that appeared in no public records. Meetings were held behind closed doors, and participants were required to sign non-disclosure agreements that extended far beyond standard scientific confidentiality. For the first time in the history of asteroid observation, portions of an object's data were withheld from the IU's public database. Light curve measurements, spectroscopic profiles, and radar imaging results that would normally be shared with the global astronomy community simply disappeared from the archives. When pressed by colleagues, officials cited calibration issues and data quality concerns, explanations that satisfied no one who understood how the observation systems actually worked. The silence spoke louder than any announcement. Whatever 31 Atlas was, it had crossed a threshold from scientific curiosity to something that demanded institutional control. The question was no longer just about what the object might be, but about what it might mean if the answer got out. The debate fractured along familiar lines, but the evidence refused to settle into comfortable categories. Some argued for natural explanations, invoking exotic mineral formations created by ancient collisions, electromagnetic anomalies in the asteroid belt's complex magnetic environment, or even the remnants of a binary system breakup that scattered unstable isotopes in unexpected ways. Others pointed to the precision of the signal, the quasicrystalline patterns encoded in light, the technetium that shouldn't exist, the coordinated swarm behavior, too structured, too deliberate, too responsive to dismiss as cosmic coincidence. Proposals emerged, each carrying its own risks and uncertainties. Send a dedicated probe for close-range investigation, equipped with instruments designed to analyze the particle swarm and intercept the signal at its source. Establish a permanent monitoring network using multiple observatories to track any changes in behavior or transmission patterns. Or maintain distance, observe from afar with passive sensors, and avoid any interaction until a phenomenon is better understood. The data offered no comfort, only questions suspended at the edge of knowledge, a crossroads between curiosity and caution with no consensus in sight. If 31 Atlas is artificial, then its presence in the asteroid belt for 170 years, undetected and masquerading as a natural object, suggests a technology capable of camouflage at a level far beyond human capability. If it's natural, then the fundamental laws governing isotope decay, crystal formation, and electromagnetic behavior may need rewriting. Either way, the universe just became less predictable and the asteroid belt less empty than we thought. And somewhere between Mars and Jupiter, a dark object continues its orbit, pulsing light into the void at 11.3-minute intervals, its particles swarm shifting in patterns no equation can predict, waiting for someone to answer, or perhaps to finally notice what it's been saying all along.